So let's take a closer look at the formation of our sun, specifically in stars in general. Remember, the claim in nebular theory is that it all started out as this giant nebula, what we call the solar nebula for our solar system, and just a nebula in general for other stars. But the idea is that this nebula had to contract. Well, why do nebulae exist anyway? If gravity's trying to pull everything together, why don't all nebulae contract down into stars? Because there's a balance of forces. Remember that every atom in this nebula has its electrons on the outside of the atom. And so every atom, as kinetic molecular theory tells us, is pushing every other atom apart. There's always space between them, and gravity, to try to push these atoms closer together, actually has to overcome the repulsion of the electromagnetic force between these atoms. But there's not enough gravity to do that because, remember, gravity gets weaker with greater distance, and these nebulae, remember, are 10 or 100 times the size of our solar system. So to start turning a nebula into a star, to start it shrinking or collapsing, something has to begin the process. Something has to give the nebula an initial squeeze to bring some of those particles closer together so that gravity increases in strength and can start overcoming the electromagnetic repulsions between the atoms. This thing is called a trigger. And there are a number of different possibilities for a trigger. The one we think that started our solar system collapsing was actually the shock wave from an exploding star, a supernova. So to illustrate that, imagine here's a star and it's coming near the end of its life and it explodes as a supernova, and the shock wave from that explosion spreads out in space, pushes the matter of the nebula together so that it's squeezed, gravity becomes a little stronger here and here, and the matter collapses down. It begins to shrink. And as it begins to shrink, more matter clumps together, which increases the gravity of that little collection of matter, which means it can pull more matter in, which increases its gravity, and you get a positive feedback to the, as we saw with the gas giants in nebular theory. And so that more and more matter clumps together and more of the nebula starts to shrink and collapse. And that's what we saw with nebular theory. But now we're going to zoom into the center of the nebula and see what's going on as we're going to turn the center of the nebula first into a protostar and then into the sun. So as the nebula contracts and heats up, the hydrogen atoms are going to move faster. Remember, this is one of the gas laws, that if you squeeze a gas, then it actually heats up. Kinetic molecular theory tells us that the temperature of an object is actually a measure of how fast the particles are moving. Why does a gas heat up when you shrink it? Well, if you've ever dribbled a basketball, or any kind of ball, and you're bouncing it up and down, and then you slowly move your hand closer and closer to the ground, so the ball is traveling a shorter and shorter distance between your hand and the ground, you know that the ball will actually start bouncing faster and faster and faster. That's because it has the same energy, but that energy is now condensed into a smaller place, and so it shows up as more speed. This is what happens inside the collapsing nebula. The particles, as they're being squeezed into a smaller and smaller volume, have the same energy, and therefore will be moving faster in less space. And as the nebula continues to collapse under the influence of gravity, the particles move faster and faster and faster. Now, at about 4,000 Kelvin, inside the very center of the nebula, what has now become what we call a protostar. It's heated up enough that it's giving off a lot of electromagnetic radiation, but mostly in the form of long wavelength infrared, what we call heat. So it's giving off a lot of heat, it's giving off some light, it's what we call a protostar, and all that energy is coming from the shrinking, the squeezing from gravity of that nebula. But at 4,000 Kelvin, we need to look at something else in the atoms. Remember, a second effect of energy on matter is that the energy can go into the electrons and bump them up to higher energy levels. This electron can go from here to here. Normally what happens then is that the electron will release that energy and drop back down. But now the nebula is getting so hot, there's so much energy being pumped into these atoms that before the electron has a chance to drop back down, it actually gets hit by more energy, gets bumped up even higher, and before it has a chance to drop back down, it absorbs even more energy to be bumped to an even higher energy level, and it keeps getting bumped up so much higher that eventually, very quickly in fact, it gets moved so far from the nucleus that the electromagnetic force from the nucleus can't hold it anymore, and the electron escapes. I've only drawn in 3 energy levels here. This really happens after the 7th energy level. But once it moves past the 7th energy level, then the electron escapes. It can't be held anymore by the electromagnetic force. And so you now have the matter of the protostar existing in a state of matter we call plasma. This is different from solid, liquid, or gas. If it's in a solid, liquid, or gas state, then you have actually complete atoms with the electrons attached to the nuclei. Once the matter gets so hot that the electrons get pulled off the nuclei so that you now have free nuclei and free electrons zipping around, you have a state of matter called plasma. Now remember that for a protostar, this matter is almost entirely hydrogen, and the nucleus of a hydrogen atom is one single proton. So what we've done is we've divided this matter up into free protons and free electrons. And we're going to mostly ignore the free electrons and see what happens with the free protons. The protons, of course, are positively charged. And so as they're flying around, whenever they approach one another, they're actually going to repel because of the electromagnetic force from the like charges. But of course, as they're getting hotter and hotter and moving faster and faster, they're going to get closer and closer to each other before the electromagnetic force can repel them. Now, what happens at about 10 million Kelvin? The particles, the protons, are moving so fast that before they can be repelled by the electromagnetic force, they get within femtometers of each other. Why does femtometer sound significant? Because it's at those distances of femtometers that the strong force comes into effect. And remember, the strong force is stronger than the electromagnetic force. And so once the nuclei get within femtometers of each other, the strong force grabs them, holds them together against the repulsion of the electromagnetic force in what we call nuclear fusion. And we have now fused 2 single protons into one nucleus with 2 protons. We've gone from atomic number 1, hydrogen, to atomic number 2, which is helium. Inside the core of the star, hydrogen has actually fused into helium, with the particles moving so fast that they get within femtometers of each other, allowing the strong force to hold them together. Now, in fact, the process is a little more complicated than that, and I think we'll mention that in the next video.